Hello, Assalamualaikum warahmatullahi wabarakatuh. My name is Aina, and today I will be presenting my final year project titled Hydrogel Production from Extracted Cellulose of Napier Pakchong, Napier India, and also Napier Kobe. This project is supervised by Dr. Norida binti Osman. Alright, so before proceeds any further, this is the overview of my presentation today. The timestamp of each part is also included, so it will be easier for you to move between sections. Alright, let's carry on with the introduction of the project. Firstly, the problem statement that has led towards the project. Problem number 1 is, common synthetic hydrogels are fundamentally different from biological gels. Synthetic hydrogels like PEG are usually stiffer and less porous than natural hydrogel. Nature's gels, on the other hand, are fibrous in architecture and porous, which allows easy transport to entire cells. This feature is required in hydrogels for it to be implemented in biomedical field. Problem number 2 is comparison of Napier India, Napier Pakchong, and Napier Kobe are not easily accessible online. Last but not least, problem number 3, there is limited exploration on producing hydrogels from self-extracted cellulose from Napier grass. Done with problem statement, now let's see the objectives that we would like to achieve by the end of this project. The first objective is to assess extracted cellulose from Napier grass, which are extracted via acid and alkali treatments. Second objective is to examine the effects of cross-linker concentration and swelling temperature to hydrogel performance. Third is to characterize extracted cellulose and produced hydrogel using FTIR and XRD on top of to study the properties of hydrogel such as its swelling abilities and tensile strength. Last but not least is to perform ANOVA, which is the analysis of variance via SAS to support findings on swelling test. Moving on from introduction, now we'll go into the literature review. We will start off with the Napier grass. Napier grass are also known by the locals as rumput gajah or sometimes Penicetum purpureum by its scientific name. It belongs to the Poaceae plant family, which is the family of grasses. You can see here from the taxonomy classification in this figure. It has strong adaptability and wide availability. And another advantage of Napier grass, it has a very short production period, usually less than a month, at a very low cost. Alright, now we have to know what is Napier grass. So, cellulose is what we want to extract from it. Cellulose is a polymer made up of glucose units joined together by condensation polymerization. And cellulose usually comprises 38 to 50% of cellulosic biomass, while others are hemicellulose and lignin. So you may ask, where did cellulose come from? So let's see the screen. Usually, cellulose can be found in the stem cells of plant, and cellulose usually coexist together with hemicellulose and lignin as depicted in screen. Now, in the second figure, we can see that cellulose is made up of beta-glucose monomer, which is linked by beta-1,4-glycosidic link. Cellulose molecules has a very straight chains, which makes them able to arrange themselves very close together, making them has a very rigid structure. Compared to starch, cellulose is more crystalline and is insoluble in water. Another advantage of cellulose is it is tough, fibrous, and water-insoluble polysaccharide. Thus, to extract cellulose, there are many methods that have been documented in research articles. So I have made a summary of the papers that I have read into this table. We have known what is Napier grass and what is cellulose. Now let's get to know what is hydrogel. So hydrogel is a 3D network of hydrophilic polymers that can swell in water and hold a large amount of water while maintaining the structure due to chemical or physical cross-linking of individual polymer chains. Looking at this figure, initially monomers are not connected to each other, but when it is cross-linked, it forms a network that enables to hold water within the network. So, hydrogels can be classified into many ways, but in this presentation, I will be only focusing according to two ways, which is the source and also cross-linking. To classify hydrogels according to its source, it can be either natural, synthetic, or combination of both, which is hybrid. And according to its cross-linking type, it can be chemical or physical cross-linked. So in this project, we'll be focusing on the natural and hybrid hydrogels, and the hydrogels are chemically cross-linked. So hydrogels in biomedical field has been widely used. It usually used in contact lenses, wound dressings, drug delivery, and also tissue engineering. Water suspended in gel matrix provides moisture which promotes wounds and scars healing. Thus, the methods on how to produce hydrogels are summarized and documented in this table. So after reviewing many research articles, it is found out that only few research papers utilized Malaysian local Napier grass. So I intend to compare the properties of Napier cultivars obtained locally. And the second research gap is there is limited studies on hydrogel production formulated from extracted cellulose from biomass. Thus, I would like to find the right formulation to produce hydrogels from extracted cellulose. Alright, moving on to the methodology of this project. First thing first is the overall research activity, which I have highlighted in which phase a certain objective is achieved. Following the overall research activity, now we move on to the flow chart of the experimental procedures, where we can see the flow of fresh Napier grass is transformed to hydrogels. And the one in pink is actually the manipulating parameters of this experiment. The first one is Napier cultivars, which we have used Napier India, Napier Pakchong, and also Napier Kobe. At hydrogel production stage, we have manipulated the cross-link concentration from 1% to 5%. And during swelling test, we have manipulated the swelling temperature from 25 degrees C to 65 degrees C. Alright, so the first part of experimental procedures is to prepare Napier grass fibers. The methods are adopted from Reddy et al.'s paper, in which the Napier grass are all washed and cleaned before sun-dried and oven-dried. It is then granulated and grinded before sieved. Only particles having 300 microns is used for treatments. So moving on to part 2, where the Napier grass have been prepared, we proceed with the extraction of cellulose single fibers, which also adopted from Reddy et al.'s paper. Firstly, the Napier grass fibers is dewaxed using toluene ethanol mixture for around 3 hours, and then it is delignified before it is treated with sodium hydroxide for 45 minutes. The last treatment is to treat with acetic acid and nitric acid for 20 minutes, and at every treatment, it is vacuum filtered and washed to remove excess chemicals. The last part of experimental procedures is to produce the hydrogels, in which we have two methods, which are method A and method B. Method A is adopted from Chang et al.'s paper, in which we have used epichlorohydrin or ECH as the crosslink agent. Meanwhile, adopting from Sun et al.'s paper, for method B, we have used MBA as the crosslink agent, and the monomers are cellulose as well as methicuric acid to form semi-interpenetrating hydrogels. This method utilizes initiators of APS and also anhydrous sodium sulfite. Alright, then with the experimental procedures, now we move on to the analysis and characterizations methodology. So generally we have 6 analyses in which both cellulose and hydrogels will undergo FTIR and XRD analysis. So FTIR is done to observe the presence of functional groups, while XRD is to determine the crystallinity of the compounds. And for cellulose, we have extra analysis, which is the yield analysis, which we calculated the cellulose yield based on the change of mass. For hydrogels, we have tensile test, which will carry out using standard ASTM 882 using a universal testing machine. So for swelling test, it is to measure the water absorption capacity, and for ANOVA, analysis of variance, it is to support our findings from our swelling test. Alright, done with methodology. Now let's proceed with the results and discussion, which I have divided into two parts, which are the first one is to discuss on cellulose, and the second one is to discuss on hydrogels. So let's start with the yield analysis. So we can see here that the color of Napier grass fibers has changed from brownish color to white after treatments, and the color actually has transformed significantly right after the first process, which is the delignification step, which uses the acidified 0.7% sodium chloride. Acidified sodium chloride is an oxidizing agent of phenolic rings which enhances lignin removal. So it is safe to say that the color change has occurred due to removal of non-cellulose components from Napier grass. Alright, so as we compare the cellulose yield of our raw materials, it is found out that Napier Kobe has the highest yield with 50%, while Napier India has the least cellulose yield at 34%. As we compare the yield with the established research papers, our Napier Kobe is considered quite high for Napier grass that is obtained locally. Alright, let's move on to the FTIR of untreated Napier grass. So this analysis confirmed the chemical composition of Napier grass fibers, and what I want to highlight here is in this region, which corresponds to the functional groups of C double bond C and C double bond O. This region indicates the presence of hemicellulose and also lignin. So as we can see here, Napier Pakchong and Napier India has quite high peaks at this region, which indicates that they have higher amounts of hemicellulose and lignin, which were removed during treatments. This results in lower yield of cellulose for Napier India and Napier Pakchong. Alright, so according to Lee et al.'s paper, the important region for cellulose is actually from 1363 to 1893 wave numbers. So that is why we only focus on that region for FTIR for cellulose single fibers. So from the figure, we can see that CSF, Kobe and Pakchong exhibit similar absorbance spectra with analytical grade cellulose spectrum. This confirms the purity of extracted cellulose except for cellulose single fibers India. The reason why I say so is because for Napier CSF India, we have extra peak here at 1513, which corresponds to C double bond C functional groups. As I mentioned before, this region indicates the presence of lignin. So it is safe to say that CSF India still has trace of lignin. Alright, so as we compare the untreated Napier grass fibers with the extracted cellulose single fibers, it can be seen that untreated Napier grass fibers has higher absorbance value than extracted cellulose single fibers. This indicates a significant removal of hemicellulose and lignin during chemical treatments. This also proves a purer cellulose in sample after chemical treatment. The removal of hemicellulose and lignin are also confirmed based on the reduction of C double bond C and C double bond O peak intensity. Moving on to XRD analysis for cellulose, the crystalline phase of CSF is contributed from cellulose, while the amorphous region is contributed from the hemicellulose and lignin. The crystallinity of extracted CSFs are comparable, with Napier Kobe has the least crystallinity at 52%. So this is expected to influence the absorption capacity of hydrogels, as crystallinity determines the strength or the atoms arrangement of a compound. Alright, now we have reached the second part of results and discussion, which is the discussion for hydrogels. So initially, we have tested the method A, but it was not successful to form a perfect hydrogels. Thus, we have concluded that method A is not suitable for self-extracted cellulose. Thus, method B is proposed. At last, we finally managed to produce a perfect hydrogels using method B. And from the screen, we can see that the 5% cross-linked hydrogels has the most opaque appearance, and actually it is the most rigid hydrogels. This due to higher cross-link agent increases the cross-link network density, and this also suggests that the 5% hydrogel will have high tensile strength. Proceeding with FTIR for hydrogels, these figures confirm the compositions of cellulose/PMAA hydrogels. But what I want to highlight here is the one in green actually corresponds to COOH groups of methacrylic acid, and the one in blue is assigned to O single bond H functional groups, which might affect the absorption capacity of hydrogels during swelling test later. So according to SRD analysis for hydrogels, we can see that there is no sharp peak is observed. Thus, it is safe to assume that cellulose underwent amorphous dispersion in hydrogel aqueous mixture, therefore producing a broad scattering features. And we can see from the table that NAPIER India hydrogels has the least crystallinity, which further proves findings in FTIR previously that there are still residual of hemicellulose and lignin contents in CSF India. And as we compare the crystallinity from La Maestro paper, it is actually quite low. And this suggests that probably the cellulose-based hydrogel will degrade easier as it has lower crystallinity. Now let's move on to the tensile test for hydrogels. Basically, there were 5 samples prepared, like listed here, but only 5% hydrogel is viable to underwent this testing machine. So the average value that we have obtained for the 5% hydrogel is the tensile strength is found to be 238 megapascal. And as we compare with the recent established papers, it is actually relatively high. And this it is safe to say that cellulose and PMAA contributed to increasing the hydrogel strength. As we cannot use the universal testing machine for 1% and 3% hydrogels, we only recorded the time that it takes for the hydrogels to be broken. So we can see here that as the hydrogel concentration increases, the time taken for the hydrogels to break increases as well. This is due to higher cross-link agents increases the cross-linking density, and this also leads to a tighter network structure. And this explains why 5% hydrogel strips took the longest time to break. Now we have reached the swelling test for hydrogels. The results show that the swelling ratio increases as the cross-link agent decreases but as the temperature increases. The reason why is the cross-link restrains the mobility of macromolecule chains that does not permit water penetration, thus it depresses the water uptake. To explain the temperature effect, the heat makes polymer chains more flexible, thus breaking the secondary interactions. When it breaks, it gives more room for water uptake. So seeing here, NAPIER Kobe absorbs the most water. This may be due to CSF Kobe has the least crystallinity, so water able to penetrate easier into the network. Also, from the FTIR, it is found out that the OH bond in Kobe hydrogels is the highest, which may be promoting the hydrophilic nature of hydrogels. Alright, now we have reached the last part of our project, which is the NO valve to support our findings in swelling test. So we can see here that the experiment is very significant as it has the p-value less than 0.001, and the model fits quite significantly, which is 0.98. And from here we can see that all parameters effect are significant to water absorption capacity as p-values are all less than 0.001. In other words, all parameters, which is the NAPIER, concentration and also temperature, influence the absorption capacity of hydrogels. All in all, it is safe to conclude that NAPIER Kobe has the highest cellulose yield, followed by NAPIER Pak Chong and also NAPIER India. FTIR confirmed purity of cellulose and crystallinity of extracted cellulose are comparable. Secondly, the absorption capacity decreases as cross-link agent concentration increases. Thus, compromises are required as high tensile strength is a trade-off for a good absorption capacity. Last but not least, based on ANOVA, NAPIER grass cultivars, cross-link agents, concentration, and swelling temperature are all influencing the hydrogel water absorption behavior. My recommendations for future work is, firstly, as the project is limited to cellulose-based hydrogels, it is recommended to apply different lignocellulosic components such as xylene, which is a type of hemicellulose, and maybe we can extract cellulose from other biomass such as bamboo and wheat straw. Secondly, as this project is limited to water absorption, maybe next time we can test for body fluid absorption such as amniotic fluid or blood, in addition to water absorption. If the hydrogel is able to absorb this body fluid, it may be widen the opportunity window for hydrogels in biomedical field. Lastly, this is a reference used in my project. And with that, I end my presentation. Thank you for listening. Have a nice day.